All right, everyone. So we have chapter 13 here, which is on mechanical waves. So we're going to learn about waves in general and learn about a lot of the concept that, can be applied to pretty much all of the waves. But specifically in this chapter, we're going to be learning and concentrating on mechanical waves. And we're going to see the difference between mechanical and, let's say, non-mechanical. All right. So generally the waves you can think of like can be broken down into two main types. So as I mentioned, right, there are mechanical waves um, and electromagnetic waves. So mechanical waves basically require some kind of physical medium. And generally the wave itself is considered to be some kind of disturbance. So, and for mechanical waves, you need to have a medium, a physical medium for disturbance and for the propagation of wave. And for example, of a mechanical wave is a sound wave, a string wave, a water wave, because no water, no wave, no water wave, right? No string, no string wave, no air molecules, no sound wave. So those are the examples of the mechanical waves. Again, they require a medium to disturb and propagate. Where you can see there's also electromagnetic waves. And for electromagnetic waves, no medium is required. That means, the electromagnetic waves can propagate through vacuum, through empty space. And perfect example of that is the light. And, for example, you can see all the stars, you can see the sun, right? Or the reflected light from the moon or other planets, because that light, which is a wave, can propagate through, space, right? Which is, basically vacuum, empty space. All right. So we will be mostly, again, concentrating on mechanical waves in this chapter. We have at least, three chapters on electromagnetic waves when we get to physics 67. So we're going to talk about electromagnetic waves, optics and all of, at least, about three or four chapters just, based on that. So here in this class, physics 66, we will be spending, a couple of chapters uh, learning about mechanical waves. So in this chapter 13 and chapter 14, basically together gives us the fundamentals, right? Foundation of the mechanical waves. All right, so what is a wave? Well, wave is some kind of disturbance that generated because of, some kind of circumstances, right? So think like this, you have a water, you throw a rock into the water, it hits the water and it generates basically a wave. So, the water hit, the rock hitting the water, acts like a disturbance, and then you see the ripples and things like that, and that basically the waves generated because of that. And when the wave is moving, the medium itself is actually not moving. Let's say what's moving, let's say, is energy and information. So that's why the wave motion, right, is energy transferred over a distance. Matter is not transferred over a distance. That means if you have like, let's say, a water wave like this, so the water actually just goes up and down, but the wave itself is then moving, let's say, to the right or to the left, right, in, one direction, and energy and information is basically moving. And by information, I mean is this, right? So when I, let's say, imagine you're sitting in a classroom and I'm talking, and information, right, there are, that, let's say, you're receiving from, me talking is basically in a form of disturbance in air and specific type of frequencies and things like that, and it's moving through air, propagates through air, reaches your ear, then converts into, let's say, information, right? And your brain basically understands what I'm saying. um, but that's pretty much all energy. Energy makes them those, air molecules, right? It's kind of like, let's say, vibrate, right? They hit each other, they transform that information until it eventually reaches your ear and your brain, right? So that you can understand. All right, so again, matter is not transferred over a distance, being it a string wave or a water wave. Medium itself is just basically allows the wave to propagate, but it's not moving with the wave. So disturbance is transferred through space without an accompanying transfer of matter. That's important to understand. And, again, as I said, right, you can think of like, let's say, important thing to understand about the wave is that wave transfers information and energy. So, and all waves carry energy. Some, like let's say if you go outside, when it's a sunny day, your skin will have the sunlight, right? So when it receives the sunlight, it starts warming up, right? Why? Because there's energy, sun's energy then absorbed by your, let's say, skin molecules, right? And some of that energy then converted to heat. So that, like let's say energy, amount of energy, then something that we're going to talk about later on. Okay. So, but that's kind of like the main thing. So all waves carry energy, and then we can eventually calculate that as well. All right, so let's see what we need for the mechanical waves. We need a source of disturbance. That means something that creates the disturbance. So as I said, right, if you're throwing a rock into the water, that acts like a disturbance. And if you have, for example, you have a string like this, and you take the left side, right, and starts oscillating up and down, what it's going to do is going to basically create a wave, which we'll see in a little bit. I have a simulation that I'm going to show you. So then some source of disturbance, and then the medium that can be disturbed, and then some physical mechanism through which the elements of the medium can influence each other. Okay, so this requirement ensures that the disturbance will in fact propagate through the medium. That means, let's say there's a little bit of a stretching and tension in the string, or the air molecules, right, vibrating back and forth and hitting each other. So those are the requirements for that. All right, so here's an example, right? So the wave is generated by a flick on one end of the rope. So you take the rope, you basically generate a single pulse. So this is known as a pulse, right? And it is then traveling to the right, even though medium itself, it just stays there. But what you have here is you're basically generating a wave by pretty much disturbing the medium, right? So you can have like let's say one flick to create one pulse, or you can continuously do that to generate wave after wave after wave. And the wave then will be moving to the right. One of the things we're going to see that when it hits actually this point, it's going to reflect back. So then actually it's going to reflect back up and then continue moving like this. So you can see, right, as a function of time, see the wave itself, right, is moving to the right with some velocity v. And in a little bit, we can also even calculate that velocity based on some of the characteristics of the wave itself. But in this case, one important thing to see that what we're doing here is to generate that wave. We moved the string up and down, which is perpendicular to the propagation of the wave, right? So that's what we have. So we have a traveling wave or a pulse that causes the elements of the disturbed medium to move perpendicular to the direction of propagation is called a transverse wave. So in a way, the mechanical waves can be, broke down into two types: transverse wave, which we just right now looking at, which is, see the medium, right? The string itself, you move it up and down to generate that wave. So wave is moving to the right, but string itself goes up and down. So this is known as a transverse wave because the wave, right, is caused by an element which goes perpendicular to the direction of propagation. So the particle motion is shown by vertical arrow, okay? All right, so the direction of propagation is shown by the horizontal. That means, the particle itself, right, the string goes up and down, where the, wave itself is traveling to the right. The other type is a longitudinal wave. So for the longitudinal waves, then instead of moving the medium perpendicular to the direction of the propagation, we move it in the direction of the propagation. That means back and forth, sort of like, let's say. So a spring or a slinky or a sound wave is a good example of a longitudinal waves. Okay, so again, so in this case, you have a traveling wave, and then the disturbance, of the disturbed medium to move parallel to the direction of the propagation. That means this is the direction of the medium, right, back and forth, where this is the direction of basically the pulse, that the pulse is moving to the right. And one of the things we're going to see here is, this is, some area of higher concentration, some area of lower concentration. That's kind of, similar to the, so like, this is our pulse, right? This is our pulse kind of moving like that. And it is again moving and changing its position as a function of time and position. So that's one of the things we're going to see. All right. All right, so here's that simulation that I promised. So we should be able to see how we can, so let's say this is pretty much, you can take like a still water, right? And then we create a disturbance. And then disturbance then generates those waves, right? Those ripples, and they are propagating, with time. So as if you continue, right, disturbing, then you're going to continue basically creating and generating those waves. So we can also look at this in terms of, so let's say if I do a graph and we continue doing this, see, you can see that the motion or the graph for the waves is very similar to the simple harmonic motion. So it's kind of like the oscillation, and then the wave is propagating, as a sine or cosine function. So it's a sinusoidal. We can also look at sort of like a side view to see that those are basically representing the water waves, right? So you can see that the water waves are, again, sinusoidal. They can have, in terms of some of those like the simple harmonic motion, characteristic, like a period and frequency and angular frequency and things like that, and amplitude, right? All of those things because of their shape. So one of the things we're going to see here is that, let's say if you talk about water wave, right? So water wave is actually a little bit of combination of transverse and longitudinal waves. So that means it's a sort of like a combo wave a little bit. So, but one thing we can see here is, for example, if you look at here, I have a sort of like a string type of, where we can then create a disturbance. So let's say there is no dumping, and tension, let's say, is medium. And we have, let's say, a reference line that I can kind of move it here. And let's say this is no end. And I'm going to create a pulse. Let's say first I'm going to create a pulse. See, if I create a pulse, see, it's moving like that. So for example, if you talk about the medium itself, so let's say, look at this marble over here. So this green marble. So what it does, green marble kind of moves up and down, and wave is propagating. Then let's do a slow motion. All right, so slow motion. And let's see. See that marble goes up and down, but the wave itself is then propagating to the right. Okay, it's propagating to the right. That means, you can, if you continuously do that, for example, say, let's say if I have this, what do? I create a disturbance. That's a disturbance that I create. Okay, and it generates a wave, and the wave is moving, but see the particles, in the string itself just go up and down, with respect to this. So then one of the things I can do here is, again, if I create this, let's say I can stop and measure, the amplitude of the wave and things like that. But for example, if I continuously do that, see, then I'm generating continuous waves. So that means, this is, up and down. See, like, let's say that green marble, the very first one, all I do is just I move it up and down, right? Perpendicular to the direction of the wave motion. And then I generate then these waves. And one of the things we're going to see here is when you're talking about then wave equation. So the wave equation then depends on a number of things. For example, let's say, again, if I reset, see right now, again, concentrating on this particular, let's say, a marble, right? So this marble right now sitting at the, you can say that, if I move this like this, so this is sitting at the, if I do the graph, right, sitting at the y equals 0 position. Okay, it's sitting equal y equals 0 position. But then when I'm generating a wave, right, depending, on the very first wave, right? So let's say where the wave is and how is it moving as a function of time and position, then position of that marble then constantly changes, that its vertical position, you can see, right? There you go. So it starts constantly changes, and then you have a second crest, right? And second wave, and so on. So then it moves up and down. And one of the things we're going to see is that, when we set up the equations and things like that, we can find out, let's say, what is the position of the, let's say, some kind of particle or some kind of, a wave and things like that as the waves, let's say, propagates to the right. So we can, measure the, let's say, the positions, we can measure, let's say, the time and all of those things. All right, so we'll come back to this again. All right. So then what we have here is this again. So you can see, like, if we go back and look at some kind of a wave that is generated, a string wave. So you can see that the wave is right now, moving, and the top, which is known generally as a crest of the wave, which is the maximum positive amplitude. Let's say at this instant, at t equals 0, is at, y equals 0, y equals, let's say a position, right? So it's at the maximum amplitude. So here's what we can do. So this shape can be represented by y x comma 0 equals f of x. Now, what does it mean over here? It means that we have two things, that means vertical position of the particle depends on two things: horizontal position and time. So when t equals 0, so usually we write it as y x comma t. And since t equals 0, so you can see, right, the second term here over there is 0 and equals some f of x, which is, we're going to have some kind of function. So this describes the transverse position y of an element of the string located at each value of x at t equals 0. Okay, so then, for example, you can see, right, t equals 0, the shape of the pulse is given by function y equals f of x. And let's say you have some point P over here, right? See, as the, crest of this wave is moving, right? As the wave itself is moving, this distance VT, and, the VT is basically described by this, delta X equals VT, remember? That, kinematic, not kinematic, but like, let's say that uniform motion equation, because we can assume that, velocity or the speed of the wave is constant. That means the wave is not speeding up or slowing down. It's always moving at constant speed. So distance or displacement can always written in terms of velocity times time. That means when it's given v times t, that's just basically the distance that this, the crest, right, traveled as a function of time. Okay. And then one thing you can see, right, see the position of this point P now is different because it was on the y equals 0, right? At y equals 0, now it is some y position. That means it has been changed, right? It has been changed by some, vertical position. Now, what it means is that the speed of the, pulse, right, is written as v. And we're going to see there are a number of ways we can actually calculate that. And at some time t, the pulse has traveled a distance vt. Excuse me. Again, this vt is the distance it's traveling. So as I mentioned, right, so we can just write down this. So this is, remember, this is y versus x, not y versus t. And this represents just the distance that wave is traveling. Okay. So then this equation, right, this position yx comma t becomes yx minus vt. Okay, yx minus vt 0. Okay, so its position is now this in terms of, like, let's say this is that extra distance that it traveled, right? So for a pulse traveling to the right, then we can write it like this: yx comma t equals f then x minus vt. And for a pulse traveling to the left, yx comma t equals f of x plus vt, where then this represents that distance it is traveling, right? Plus or minus inside represents specific direction. And the negative inside the argument is always for the object moving in a positive x direction, and positive here is object moving in a negative x direction in this particular case, since we're considering, x. All right, so this function is known as a wave function. You can see, right, the wave function represents the y coordinates of any element located at position x at any time t. Okay, and the y coordinate is the transverse position. All right, so then again, because as the wave is moving, we can assume that its shape does not change. So then even though it is traveling some distance vt to the right, it is still, basically same shape and technically same wave. So in order for us to represent that, that even if it's traveling to the right some distance vt, it's still same shape, then that's what we do, right? So that's why we have x minus vt. So f of x minus vt is basically, in a way, we can say that this is exactly same shape as the one that we started with. That means that, what we're saying here is the argument of the function, right, still should be or must be the same. All right, so again, this is again known as a wave function. So wave function represents the y coordinate of any element located at position x at any time t. So now we have two variables, right? So we have x and time. That means, position, right? Vertical position basically depends on two variables in this particular case. So the y coordinate is the transverse position, right? Transverse position of the element itself. So now, if t is fixed, then the wave function is called the waveform. It defines a curve represented the actual geometric shape of the poles at that time. So that's kind of like, let's say, in terms of drawing it, something like that. All right, so let's look at an example over here. Again, remembering that one of the things we have here is the negative in front in the argument represents, specific direction and things like that. So let's say we have an ocean wave with the crest to crest distance of 10 meters. Okay, so which can be described by a wave function yx comma t equals 0.8 sine 0.628, then x minus vt, where x and y are in meters, t is in seconds, and v here is 1.2 meters per second. So you want to sketch this at t equals 0 and at some later time, 2 seconds later, basically at t equals 2 seconds. And then we're going to compare the graph, talk about similarities and differences and how was this wave moved, let's say between graph A and graph B. All right, I think it's probably would be better to come back to this example after I explain to you, let's say, what is a crest, like let's say the wavelength and things like that. So we will come back in a little bit and, tackle this example. Because, even though I mentioned that in the simulation, I want to kind of talk about the actual graph of the position versus vertical position, right? Versus horizontal position, or vertical position versus time of the wave, because we are getting y as a function of x and comma t. That means, in a way, y can be graphed with respect to two different variables. One of them is, y versus x. That means this graph represent the, let's say, how the wave itself is moving as a function of position. And we assume, again, this is a continuous, not a single pulse, right? It's a continuous wave. So, and as you could see, right, from that water wave and from other, a simulation that I showed you, it is a sinusoidal graph. That means the object, even, you're looking at the string shape of the string, right? When you create a wave, it is basically sinusoidal. Now, there are, 2 points of interest. Generally, the highest amplitude, remember, this is known as the amplitude, right? So A is for the amplitude, and then this is negative A. And generally, the highest amplitude is known as a crest. So the crest of a wave is located at the maximum displacement of the element from its normal position. That means, that's basically the highest positive displacement. And then we have a trough, which is then the lowest right? So it's a negative amplitude, basically the lowest, position relative to that normal. Normal, we basically assume that, let's say if it was a string was basically something like that. And then when you start oscillating, it goes up and down. So when it goes up, reaches maximum displacement, it's a crest. Down, then it's a trough. Okay. Remember one thing, A itself, the amplitude, always a positive quantity. Okay, so that's why I put A as a plus A or minus A, indicating if it's a crest or a trough in a way. All right, so then if we then take a distance of one crest with respect to another crest, or one trough, another trough, that distance basically represents a shape of one wave, what we call one wave. So let's say here's crest one. So then this shape here going from one crest to another represent one wave. And that length, actual length, right? So basically the length, horizontal length is known as a wavelength and represented by Greek lambda. It is in units of meters or centimeters, depending, like, let's say what's measured, but measurement of length basically. And if you're doing again y versus x, then from one crest to another crest, that basically represents the wavelength. Okay. You can also look at in terms of going from one trough to another trough, or from one position to another position that repeats itself, right? So if you go from here to there, that's repeating itself. Go from here to there, that's repeating itself. That means, any two repeating point, is a wavelength. We can also do this type of graph for the, for our wave and, the matter, right? In terms of y versus t, very similar to the simple harmonic motion graph, right? Y versus t. So in this particular case, again, we have the same thing in terms of it's a sinusoidal graph. It just, when you go from one crest to another crest, or any, 2 points, right? 2 repeating points, then it represents the time interval, right? Going from, that means how long does it take for, let's say, for this crest to go from here to there, okay? And that is known as the period t. So you can say, right, the wavelength is the distance from one crest to the next, and then the period is the time interval requires for 2 identical points of adjacent waves to pass by a point. That means if I'm considering this point over here, point of interest, then I have one crest over here. So how long will it take this crest to reach that position? And that is the, period t. Okay. So remember, the period in this case is basically identical to the period in a simple harmonic motion, right? That means I can say then if I have the period, then frequency can be calculated from the period, 1 over the t, and also angular frequency can be calculated from the period, 2 pi over the period. That means, we have those quantities as well coming back because, they represent sinusoidal, shape and sinusoidal motion and things like that. So that means period and frequency and angular frequency, all of those things coming back from the simple harmonic motion chapter. What's new is then this type of graph where position versus vertical position versus horizontal position, because wave is moving as a function of horizontal position. And then we can also use, that to calculate, let's say, the wavelength. All right. So as I mentioned, right, we can have a frequency, which is the number of crests or any points on the interval that pass a given point in a unit time interval. That means, frequency represents how many crests go through that point in 1 second. Is it just one crest or 100 crests or 1,000 crests, right? And then, like, let's say that unit, right, hertz can tell you that, right? Let's say 500 hertz means 500 cycles each second, and so on and so forth. So again, the units for hertz, units for frequency is either, 1 per second or second to the -1 or just hertz, right? So that's the units for the frequency. And again, it's the same thing that we've been using all this time. So same kind of, like, let's say, idea from the simple harmonic motion, even then before that when we were using the period. All right, so now, one thing we have here is you can kind of like show this in terms of if it's a traveling wave. So you can see, right, the brown curve represents a snapshot of the curve at t equals 0. Yeah, so basically that this is at t equals 0. And look, let's, for example, let's look at the, in terms of, I guess, a crest, right? So a blue curve represents the wave at some later time t. Okay. And then you can see, right, once it's traveled this distance VT, you can see that basically the shape pretty much repeats itself, right? So that's why in a way then we could, use that function, right? F of x comma t is equals to f then x minus vt to kind of go back to the same, represented sort of like a same shape for the graph. By doing that, then we can, and since it is moving to the right, I am writing as negative x minus negative vt, right? Because, you can say, right, after exactly this, traveling this distance, we have exactly same shape. So we can put everything then together, because one of the things I can have, if I come back over here, let me kind of, write it down here. I can also look at it in terms of this. So I have y as a function of time. Then this is, let's say, they're representing the wave when it is, let's say, using that graph in terms of for the position, right? For the position versus time. Remember, it is technically similar in terms of a cosine, omega t plus phi. But now we have a new graph, right? So this is kind of going to be used along with new information where you have the vertical position versus x. Now, again, so now if you're talking about this specific type of graph where you have a y, x, comma, t, the waves traveled with a specific speed, which is usually known as a speed of the wave. Okay, and the speed depends on the properties of the medium being disturbed. Now we're going to write this wave function in terms of then a sine 2 pi lambda then x minus vt. Again, lambda is the wavelength, and x minus vt is basically that function representing in terms of the shape is basically repeating after every distance vt. So this is for a wave moving to the right. Again, the negative indicates that this is moving to the right, and if it's a positive over there, then you have a wave moving to the left. Now, there are a couple of new things that we have. For example, this ratio over here, 2 pi over lambda, this ratio is known as a wave number or angular wave number. So k equals 2 pi over lambda. So the units are radians per meters, because 2 pi is in radians, wavelength is in meters, so radians per meters. That means this is in terms of then 2 pi over lambda. And we also have another thing, remember, it's an angular frequency, which is omega equals 2 pi over the period, or 2 pi times f. So then in a way, one thing we can do here is if we go back to that previous equation where y as x comma t equals a sine of 2 pi times lambda x minus vt. All right, so we have this equation. So this becomes a sine of then 2 pi over lambda x, then minus 2 pi over lambda times vt. Okay, now what I have here is if I combine this ratio of v over t, v over lambda, this is nothing but speed divided by the distance. And speed divided by distance, if you remember, right, equation for the speed equals to distance over time. But see how long it takes for the wave to travel one wavelength of a distance is exactly equals to the period t. Okay, so it's equals to exactly period t. That means this ratio of v over lambda is then equals to 1 over the period. That means if I come back again, I can rewrite this as a sine of 2 pi over lambda times x minus 2 pi. See, it's v over lambda, and v over lambda is 1 over the period. So 2 pi over the period times t. Okay, so technically then this is my equation. And what I get from here is this. 2 pi over lambda is the wave number k. And 2 pi over the period is the angular frequency omega. So that's why then we can rewrite this in terms of a sine kx, replacing 2 pi over the lambda with k, minus omega t, replacing 2 pi over t with, omega, angular frequency. And this is, in a way, just more compact version of this equation. Y equals a sine kx minus omega t. All right. One thing we have then, as I mentioned, this. So when you have the velocity of the wave, you can calculate this in terms of the wavelength divided by the time, right? Distance over time. So how long does it take to cover this wavelength of a, distance, one wavelength of a distance? Well, the time is the period. That means this is one version of a, equation to solve for the speed of the wave. Wavelength divided by the period. If you have the wavelength and the period, you can do the ratio and find the speed of the wave. But we also know that the 1 over the period is also frequency, right? Frequency is 1 over the period. So we can write this as wavelength times frequency. That means this is another way of writing this particular, speed of the wave, which is basically written in this. But I want you guys to see that there are a number of ways you can calculate this speed, wavelength times frequency or wavelength over the period. But also we can use this. Remember this equation, right? This equation that relates wavelength to the wave number and period to the angular frequency. That means if I rewrite those, I'm going to get this. Wavelength equals 2 pi over the wave number. Period is equals to 2 pi over the angular frequency. And using this ratio or wavelength over the period, which is then 2 pi over k over 2 pi over omega, where 2 pi's cancel out, we get omega over k. That means this ratio is also equals to omega over k. 3 different ways you can calculate the speed of the wave. From wavelength and period, first equation, wavelength and frequency, second equation, and then angular frequency and wave number as a third equation. All right, so then here's what we have. If x is not equal 0 at t equals 0, the wave function can be generalized to y equals a sine kx minus omega t plus phi, where phi again is called the phase constant. Okay, that means those are, let's say general forms of the wave function in terms of there is a, wave number and x. That means it's moving as a function of position, it's moving as a function of time. And this just represents if your wave, right, let's say position is not x equals 0 at t equals 0. That means we have basically a phase constant. Kind of similar to, let's say, when the simple harmonic motion, right? When you don't start from x equals a, because x equals a was basically our, phi equals 0, let's say position. And then when you let go and then start the timer at a little bit later time, then phi was no longer 0. It was like pi over 2 or 3 pi over 2 or pi, depending on where the object was at t equals 0. All right, so now let's go back and look at this example over here. So we have ocean waves with a crest to crest distance of 10 meters. Now we know what that is, right? Crest to crest distance of 10 meters. We know what that distance represents, right? That's just basically the wavelength. Crest to crest distance is just basically one wavelength. And we're given this function as y x comma t equals 0.8 sine 0.628 x minus phi t. That means in a way I can, compare this to this general equation, a sine, remember it was 2 pi over the wavelength, right? Then x minus phi t. We kind of started with this, right? That means, this is given in terms of this format. So we can see then the speed is given with 1.2 meter per second. And then you can, in a way, kind of plug all the information from this function. All right, so that means my A is 0.8 meters. All right, so 0.8 meters because it says X and Y, everything is in meters. So this is my amplitude. Okay, that means, and my wavelength here is 10 meters. Again, because of that information we were given. Okay. So then in terms of looking at this, right, part A says sketch yx comma t at t equals 0. Okay. And it's later time 2 seconds. So then I can graph this where y as a function of x. Well, I know one thing, right? It's a sine function where, you know, going from, you know, let's say one position to another position is 10 meters. That means if I do this example, for example, let's say if I do, you know, 5, 10, 15, let's say 20, my graph then going to be like this. Again, why? Because, let me try to do it a little better. And then going like this. Because see, going from one position to another position of the same wave has to be 10 meters because that's my wavelength. So let's say this is something, you know, for my wave. Y in meters as X in meters, something like this. And then I'm going to do in terms of 2 seconds later. All right, so then what I have here is this, right? So in terms of 2 seconds later, my wave moving at the speed of 1.2 meter per second. So then I can say in a way that, you know, delta X is equals to V times T. So, you know, 1.2 meter per second times 2 seconds. So I'm going to get 2.4 meters, right? So that means, let's say this particular, let's say this part of the wave now moved exactly by 2.4 meters. Okay, that means now what I can have here is basically this shape is just switched by that much, right? So 2.4 meter there, 2.4 meter there, 2.4 meter there, and things like that. That means, you know, in terms of what I will have here is something like this. So this will be then my graph. And, you know, this basically you can see, right? Okay, my graph, I need to make sure that I'm kind of keeping the same amplitude and things like that. So this is that VT distance, right? It's moving VT distance, right? But, you know, the shape still exactly the same. Okay. So compare the graphs in part B with the part A and explain similarities and differences. Again, same amplitude, right? So it's going to be the same amplitude and same wavelength. It just basically it's shifted by this 2.4 meters, right? Which is basically it's shifted by this, you know, VT distance. And it says then how has the wave moved between graph A and B? Again, same thing, right? It has been shifted by exactly 2.4 meters. All right, so now we can go back. Okay, so we were here and then look at then some extra examples here. So what we're given here is this. So we have a wave function for a traveling wave on a taut string is in SI units, right? So yx comma t equals 0.35 sine 10 pi t minus 3 pi x plus pi over 2. So our goal will be to what are the speed and direction of the travel of the wave? What is the vertical position of the element on the string at t equals 0, x equals 0.1 meter? What are the wavelength and frequency of the wave, and what is the maximum transverse speed of an element of the string? All right, so we take this and we write it general equation so we can kind of compare it, right? So yx comma t equals then a sine of, and then we have kx minus omega t plus phi. And then one thing we can see here is there already a little bit of, you know, discrepancy over there because the way we have this written, right? So it's 10 pi t minus 3 pi x. That means, this is basically that term over here and it is negative. So we don't want it to be negative. So we have to kind of rearrange it. So, it is, given in the way that we want. So, what we can do then, we can write it so that 3 pi x is a kind of like a constant quantity, right? So using this where, sine of theta equals negative sine of negative theta. Because like, let's say, assuming that, our argument inside is, negative, right? So which can then also be, written as sine of to basically change that, right? So we have to add a factor of pi. That means, to make that in terms of the way we want. So it becomes negative theta plus pi, okay? That means what we need to do here is we take our function, yx comma t, and add pi to that. So it's 0.35, then sine, then negative 10 pi t plus 3 pi x, then plus pi over 4, then plus, sorry, minus pi over 4. So pi, so plus pi minus pi over 4. Sorry, plus pi over 4, because that's what we have. Then we're adding this. Okay. So we basically get this, and this is going to be, sorry, so this is then can be, let me write here, yx comma t equals then 3.5, sorry, 0.35 sine of then negative 10 pi t, or you can, in a way, you can kind of write it already the way you want, which is 3 pi x minus 10 pi t, right? And then plus pi minus pi over 4. Okay, so we basically end up with this. All right, so then from here, we can look at it in terms of what we have. So part A, then we have, not that we have this, right? For part A, we have what are the speed and direction of the travel of the wave. Okay, so we can do this in terms of the, one of the versions of the, velocity. But from here, you can see that, let's say, what are the quantities that we want? So like, let's say, see, this is 3 pi is basically nothing but if I'm comparing this to, kx minus omega t plus phi, right? So that means my k here is 3 pi. So, and my omega here is then 10 pi. So since I'm given those values directly, then I can just use this version of the speed where it's, omega over the wave number. I can use those to calculate wavelength and frequency or the period, but it's just easier to do it from here. So this is then 10 pi over 3 pi. Okay, right? Pi's cancel out, and you get then 3.3 meters per second. And this is basically in the I-hat direction. The wave is basically, because we converted, right? So the wave is moving basically to the right. So that's for part A. For part B, it says, what is the vertical position of an element of the string at t equals 0, x equals 0.1? Okay. That means we just basically add those two together, right? So for part B, we say, okay, y when x is 0.10 meters and t equals 0, using that, original equation. So 0.350, then sine, so 10 pi times 0 minus 3 pi times 10.1 meters plus pi over 4. Assuming that we're using radians, we will get negative 0.0548 meters. All right, so this is going to be the answer for that, which is about, 5.5 centimeters. And it's negative, means basically just below the reference line. All right, so part C says, what is the wavelength? For wavelength, then what we use a wave number. because we know that wavelength equals 2 pi over the wave number, and it's 2 pi over the 3 pi. So, you know, pi's cancel out, and you have 2/3. So we get 0.667 meters. For part D, what is the frequency of the wave? Well, for the frequency, we can use that omega equals 2 pi f. So f equals omega over 2 pi. So it's 10 pi over 2 pi. So it's basically just 5 hertz. All right, so for part D, what is then? Okay, I guess like, you know, the last part, it says, what is the maximum transfer speed of the element of the string? So for this one, then we have to, you know, let's say find the velocity, which is basically taking the derivative of this function. So velocity is equals to derivative of the y with respect to t, right? Derivative of position. So then this is going to be basically 0.35, which is pretty much omega a, and derivative of sine is cosine. So or thing like this. If I do it, becomes omega a cosine times the argument, right? Which is then omega is 10 pi. Amplitude is 0.35. And then cosine of then 10 pi t minus 3 pi x plus pi over 4. And then just basically using this. And if you remember, right, for the cosine, the coefficient, right? So basically this is in front of the cosine function is what we use as a Vmax. It means Vmax is, you know, omega times A. So then I can say Vmax is omega 10 pi times A 0.35. And we're going to get 11 meters per second. So this is the maximum speed. So 11 meters per second. All right, so all right, so going to the next example. So here we have write the expression for y as a function of x and t in SI units for a sinusoidal wave traveling along the rope in the negative x direction with the following characteristics. Amplitude is 8 centimeters, wavelength is 80 centimeters, frequency 3 hertz, and y, function y when x is 0 at some time t equals 0, and at t equals 0. So basically that's what we're given. So let's do that part. So then remember, so our goal here is to do this, right? Y, you know, x comma t equals a sine kx minus omega t plus phi. All right. So this is what we have. And right now, we need to find the amplitude, which is given, wavelength, which is given, frequency, which then we can use. Wavelength will be used to find the wave number. So it's 2 pi over the wavelength. So 2 pi over 0.8, find the wave number, which is 2.5 pi radians per meters. Same way we can use frequency to find the angular frequency, which is 2 pi times 3 hertz, which is just 6 pi radians per second. And if let's say displacement is 0, right? So that means y at x equals 0, t equals 0. That means the position when x is 0, t equals 0, then this implies that phi equals 0. Okay, phi equals 0. That's because we can do this, right? So if y equals 0, then equals to a sine of then k times 0 minus omega times 0 plus phi, which means 0 is equals to a sine of phi, and under which condition, you know, sine of phi is 0, because it cannot be due to a is amplitude, it's not 0. So a times sine of phi is 0 only if phi is 0. All right, so using all that, then we can come back and write this equation. Y as a function of time, right? So, sorry. So y is equals to, as a function of time and position. So it's 0.08 for the amplitude, then sine of kx, and k is 2.5 radians. So, so 2.5 pi x minus then 6 pi t, and then plus 0. So we can just say like that. And that's basically our, you know, answer for part A. All right, so part B says, what if? Write the expression for y as a function of x and t for the wave in part A, assuming y x comma 0 equals 0 at the point, you know, x equals 10 centimeters. Which means for part B, the phase constant is no longer 0. Remember, here phase constant is 0. When at t equals 0, x equals also 0. That means when, you know, it means, you know, y x equals 0 comma t equals 0 equals 0, then phi is 0 because of the, you know, what I showed you over here. But in this example, what I have here is this. So y is equals to 0 when yx comma 0, like that. T equals 0, but x is not 0. Okay. So that means going back to this, you know, this general equation, right? So looking at this general equation, so we can then try to, you know, solve it. We're saying that y, which is equals to 0, and is equals to then a sine, you know, kx minus omega t plus phi. And in this case, what I have here is 0 is equals to 0.08 sine of, then the x is 0.1, which is 2.5 pi times 0.1, then x, oh, sorry, x is already 0.1, then minus 6 pi times t, because remember, in a way, we're saying that this is 0 when y is, you know, 0.1 comma 0, and then plus phi. All right, so which gives us 0 equals 0.08 sine 2.5 pi times 0.1 becomes 0.25 pi, then plus phi. Okay, that means what we do from here is pretty much, let's say, solve it in terms of finding the phi, which in a way you can see, like, let's say the idea here is this. So I can easily divide both sides by 0.08 because the other one is 0. So this becomes 0 is equals to sine of 0.25 pi plus phi. Now the idea here is this, right? So under which condition sine of its argument is 0? Well, when its argument equals to 0, right? That means when 0.25 pi plus phi equals to 0, that means phi here is equals to negative 0.25 pi. That means only under this condition, the argument of the sine is 0. If the phi is, or phi is negative 0.25 pi, And that means, you know, we can then come back, right, to the general equation and write it in terms of then this, you know, phi. All right, that means I can say that, all right, so then y, you know, let's say x comma t, you know, just general, right? So then is 0.08 sine of 2.5 pi x plus 6 pi t, then minus 0.25 pi, which is then the phi. And that's the answer for my last part, part B. All right. All right, so next we're going to look at specifically string and string acting as a medium to generate a wave. Because one of the things we have about the string wave is that when the string is used to generate a wave, we have to deal with also this level of tension that we have in the string, because the string itself can be stretched a little bit. So you can see, right, so there's technical level of, you know, tension along the length of the string. And also one of the things we have here, if let's say if this is a length of a string that also has a mass m, and in this case the string is not massless, it has a mass. And one thing we can do here is the length and mass can be used to calculate what we call linear mass density of the string. So this mu, quantity mu, which is not the, you know, let's say a friction coefficient, this is known as mass of the string divided by its length, units of kilogram per meters. So this is then linear mass density. So linear mass density. And this basically represents how the mass of the string, you know, basically spread out over the length of the string. And usually this is like, let's say, we assume that this is a uniform distribution. So the mass is uniformly distributed over the length of the string. But because there's also a tension, so then what we can do, we can calculate the velocity only for the string waves as square root of, and I'm going to put it like this, f of t, which is the tension force, so that you don't confuse this with a period t. So it's f of t, then divided by the mu, which is then this linear mass density. Okay. Only for the string, we can use this equation. We can't use, you know, this equation for other things because, you know, it's specifically in terms of the tension in the string, and then the linear mass density, which is the length of the string, mass of the string, and things like that. You can still use this to find, you know, let's say, or find this, you know, the velocity or the speed of the, you know, string wave using the general wave times wavelength times frequency, or wavelength over the period, or angular frequency over the wave number. All of those work. It's just a one extra equation for the, you know, relating the speed of the wave to the, you know, the tension and the linear mass density. All right, so let's look at an example here. So an Ethernet cable is 4 meters long. The cable has a mass of 0.2 kilograms. A transverse pulse is produced by plugging one end of a towed cable. The pulse makes 4 trips back and down and back along the cable in 0.8 seconds. What is the tension in the cable? All right, so we want to know the tension, assuming that right away we are told that the length here is 4 meters. The mass here is 0.2 kilograms. Okay. And also we're told that it goes basically, it makes 4 trips down and back along the cable in 8 seconds. So, which means that we are kind of given the length that wave is traveling, right? Let's say, because, so I don't know, so let's say, let me have this as a cable like this, right? So the length here is 4 meters, nothing like this. So we are told, so it goes down and back. So it goes down 4 meters and back 4 meters. that means distance for each trip is basically 8 meters, right? 8 meters because it goes up and down. But it does 4 trips. That means the total distance is 4 times 8, which is total distance is basically 32 meters. Okay. Now, which means then to find the tension, I have to use this equation. Velocity of the string is equal to square root of f of t divided by mu. All right. So I can find v, even though I'm not given the wavelength or thing like that, but I know, how long, let's say it travels, right? The total for how long and the total distance. So I can just use the good old equation where it's distance over time. And the distance is basically 32 meters. And the time here is 0.8 seconds. So if I do that, I'm going to get the velocity as 40 meters per second. Okay. So, and also if I have a length and the mass, I can also calculate the mu, which will be the 0.2 kilograms divided by 4 meters. So we're going to get 5 times 10 to the negative 2 kilogram per meters. That means I have velocity, I have the mass density, and I just need to find the F of t, the tension force. Well, all I do here is this. So I take and square both sides. Then what I have here is then I have v squared equals then F of t over mu. Then rearrange where F of t equals v squared times mu. Since I have already v, which is 40 meter per second squared, and I have mu, 5 times 10 to the negative 2 kilogram per meters, then I can calculate this to be 80 newtons. All right, so that's then the tension in the string, in the rope cable. All right. We also talk about that sound wave as being longitudinal wave. So because when air molecules, let's say allow the wave to propagate, the molecules go back and forth, not up and down, but back and forth in the direction of the propagation of the wave. So they travel, a little bit forward, a little bit back. So basically they create, we're going to see in the next slide, that they create this, regions where there's more density and less density and things like that. All right. So you can see, right, they travel through any material medium. The speed of the wave depends on the property of the medium. And that's also an interesting thing because, so when we talk about sound, we think of like, let's say sound in air, but you can also have sound in water, sound in metals, right? Sound in other different type of medium. And how fast the sound is moving basically depends on the medium. And also depends on the temperature as well. So that's another thing. But for example, the speed of sound in air around, like let's say room temperature is 343 meters per second. So let's say this velocity of the sound at the temperature approximately, let's say 20 degrees Celsius, it is 343 meters per second. Okay. But this velocity can change depending on the medium. So let's say in water, it's actually moving much faster, about, I think about 4 times faster. So in water, the sound actually propagating faster because there are more molecules, right? It can use to propagate. Okay. So in terms of then here, what we can do is think of like, let's say some kind of compressible gas in a piston. So think like this. So this is kind of like simulating what the sound wave kind of looks like in terms of like, let's say air molecules and things like that. So think like this. So you have some kind of a gas, and then there's a piston. And then one thing you can do that you can basically use that, you move that piston back and forth. So imagine that if you compress the piston, so basically move it to the right, so compress the gas. And as you do that, then basically the gas is kind of like, let's say, starts moving because you basically, compressing, right? This region is more compressed. And then let's say you can see that this compressed portion kind of, more dense portion will start moving with some velocity v, okay? That means before, when the piston is suddenly moved to the right, the gas just in front of is compressed, and the region is called compression. So this is known as a compression, that region. When the piston comes to rest, the compression region of the gas continues to move because we were pushing it. So it's going to continue moving, and it's going to move with some kind of velocity. All right. So then if you move that, piston back, okay, so if you move the piston back, you can create what we call a rarefactions. Okay. So this is then, what it does, it again, changes the density in the fluid. And what we have is then you generate basically regions where they're more dense, and then regions where there's not dense. So density, high density, low density, high density, low density, and things like that. And the distance between two successive compressions or two successive rarefactions basically is one wavelength. So in a way you can think like this. So it becomes like a, crest and a trough, crest and a trough, crest and a trough, something like that. So, and you can see right from one crest to another crest is basically a wavelength, or you can say from one compression to another compression. All right. And, those molecules, right, the gas, when it oscillates, they oscillate parallel to the direction of the wave. Wave is moving to the right. Molecules also fluctuate right or left, which is parallel to the direction of the wave. All right. So, then because of that, because let's say the air molecules can be used to propagate, sound, and it's, basically it's a sound wave with very specific, let's say velocity and thing like that, then we can also have what we call this Doppler effect, which is apparent change in frequency or wavelength that occurs because the motion of a source or observer of a wave. When the motion of the source or observer is toward the other, the frequency appears to increase. And when the motion of the source or observer is away from one another, the frequency appears to decrease. Right, so this is going to be like a demonstration of the Doppler effect. So generally, you probably have, seen or experienced the Doppler effect when you have some kind of source, like a siren or something like that. When it's moving toward you, the frequency or the pitch of the sound changes when it's moving toward you. It starts basically higher pitch, but then kind of lower pitch when it's moving away from you. So kind of let's, see this here.
The Doppler effect. In Sheldon's words, it's the appearance.
All right, so let's continue then. So that means the perceived frequency of a car horn as the vehicle travels toward you is higher when it moves away. So again, this is an example of what we call Doppler effect. After, I think, Christian Doppler, who recognized that this effect, how it changes the frequency, we call it apparent frequency because technically the car horn or siren doesn't really change the frequency. Is it moving toward you or away from you? As an observer, it appears to be changing for you because of the reference frame, sort of like, let's say. So the Doppler effect for sound is experienced whenever there is a relative motion between the source of sound and an observer. That means if you're an observer and the source, like siren or a car horn, moving relative to you, or you are moving relative to the car horn or the siren, or both of you moving relative to one another, then this Doppler effect can be experienced. All right. So there are two things basically happen. So let's say in this case, imagine you have a source that is at rest, and let's say an observer is moving toward the source. So let's say here, consider observer moving toward the point source with speed VO, V of the observer. The source remains stationary relative to the air. So represent the waves with a series of circular arcs concentric to the source. Those are basically the, let's say the wave front of the source. That means you can think of like those are the representation of the sound wave moving. So let's say here's a crest, here's a trough, crest, trough, and things like that, right? So those are basically the sound waves moving in every direction, right? So that's why you can hear the sound in front, in the back, right, in the sides and things like that, because it's moved like a 3 dimension. So let's say when This is basically, if you're standing there and looking at the source, this is what happens to what appears to be what you see basically. But if you're moving toward that, in a way, you're moving toward the source. So it seems like the waves that are moving toward you become compacted a little bit. Okay. So the distance between adjacent wavefronts is the wavelength, and the speed of the sound is always going to be V, and it's always going to be 343 meters per second. Then the frequency is F and the wavelength is lambda. All right, so you can see, right? When the observer moves toward the source, the speed of the waves relative to the observer becomes basically, this is one of the relative velocities, right? So it's velocity of the source plus velocity of the observer. Because if the sound is moving toward you and then you're moving toward the sound, that means in a way sound moving faster toward you, right? Than if you were basically at rest. So the wavelength is unchanged. So the frequency heard by observer F prime as the observer moves toward the source is then changes or appears to be changing. So we're going to call it F prime. So F prime equals V over lambda prime. Okay, so, and if we kind of rearrange this, so we're going to end up with then, since using this equation where lambda is equals to velocity over the frequency, right? So kind of like using that equation. So then that means, you know, if you have 1 over lambda prime, this basically in terms of this, right, becomes frequency over the velocity prime. So then velocity prime is this one, right? V plus V naught. But, you know, since you're changing here, it becomes, you know, V minus Vs, because this is for the source rather than for the observer. So in any case, the frequency heard by the observer, F prime, as the observer moves toward the source, is then basically given with this equation. That means you can use this equation to calculate the observer moving toward the source. And here's an example where the considers the source in motion while the observer is at rest. All right, so let me actually kind of go back here. I think I have the wrong equation here. So for the frequency F prime, when the observer is moving toward the source, is actually given as, that's why I'm kind of like let's say here I have, in terms of V plus V naught, V of the observer, over V times F. Okay, so this equation, actually we're going to see this is when the source is moving toward the observer. Okay, so this is the equation when the observer moves toward the source. All right, so which is V is for the speed of sound, plus V of the observer divided by V, which is the speed of sound, then times actual frequency of the source. And then what you will see here, the apparent frequency will be different if you're moving toward the source. All right, so we're going to see that the second equation is actually when the source is moving toward the observer. So let's say here you have an observer at rest, and then the source is moving toward the observer. And then what you can see, right? So here, if it's moving toward the observer, the wavelength is different, you know, if you compare to another observer with respect to whom the source is moving away. So then you can see, right, the wavelength is longer, where here the wavelength is shorter for the observer A. Okay, as the source moves toward the observer, the wavelength appears shorter. As the source moves away, the wavelength appears longer. So, and if you put everything, you know, in the equation, right, if the source moves toward the observer, crests detected by the observer are closer together than if the source were at rest. Okay, because, you know, if it's moving toward you, then basically the sound that it generates plus the fact that the source is moving toward you, it appears to be, you know, that the wavelengths are shorter. If the wavelengths are shorter, then, you know, frequency obviously will be affected by that. So that's why wavelength lambda prime measured by the observer is shorter. So during each vibration, the source moves a distance, est equals Vs over the frequency, and the wavelength is shortened. So then again, using this equation, f prime equals V over lambda prime, then we end up with this equation. So where this is, f prime for the for the source moving toward the absorber. So this is source moves toward the absorber. Source moving toward the absorber. Then you can use this equation. Again, so this is assuming, these two equations that I just showed you, right? So basically this one, right here, this is assuming that the source is at rest, absorber is moving toward the source. And then this one is absorber is at rest and the source is moving toward the absorber, let's say. And then we can use that equation. Obviously, you can use this equation even if the source is moving away from you, right? If let's say the absorber is at rest and the source is moving away from you. But then you kind of have to, be careful in terms of the signs, because in that case, the sign is basically changes if that's the case. So I will talk about that. Now here's a more general equation. If both source and absorber are in motion, then you can use this equation. F prime equals V plus V naught over V minus Vs. And this is V absorber, right? Times frequency. Now the sign depends on the direction of the velocity. So a positive value is used for motion of the absorber or the source toward the other. And the negative sign is used for the motion of one away from one another. That means in a way you can just basically talk about, think of like that, right? So the positive value is used if the motion of the absorber or the source toward each other. Okay, that means, for example, VO and VS are positive, and that means, let's say this VS, if you're given that the source is moving at 5 meters per second, let's say, if it's moving toward the absorber, then it's plus 5 meters per second. If it's moving away from the absorber, then it's minus 5 meters per second. That means you plug in here minus 5 meters per second, so it becomes V minus minus, so ends up being V plus Vs. That means this, you use this, if you're given the speed, right, you use positive for the speed, and because this negative is the part of the equation. What this talk about, positive value or negative value is the value of the velocities. That means if the velocity of the source, is for the source that is moving toward the absorber, you take that to be a positive quantity. If they talk about the source moving away from the absorber, so you take the speed and make that as negative. So that's kind of, sort of like what we're doing. All right, so then again, so you can write convenience rule for the sign. The word toward is associated with an increase in the absorbed frequency, and the word away from are associated with a decrease in the absorbed frequency. So that's kind of like what you can think of like that. So let's say 200 hertz is the original frequency. Then f prime will be think like this. So f prime, which is appeared frequency, will be greater than original frequency for this first case, if it's basically moving toward the absorber or source. But then f prime is less than original frequency for the case when the source is moving away or the absorber moving away from the source. So basically they're moving away from one another. Okay, so and the Doppler effect is not just for sound, actually it's true for all waves. It's just sound waves are more obvious ones, and we can see the effect of that and we can hear the effect of that and things like that. So that's why usually Doppler effect is done in terms of the sound waves, but you can do also for the light waves. That we use that to see if the star is moving toward us or moving away from us by looking at the shift in frequency and wavelength. All right, so again, so this general equation, right, f prime is equals to V plus VO over V minus Vs times f. And you can see, right, so if let's say if absorber is at rest and this is 0, but if it's, let's say, if then the source is at rest and this is 0, right, and so on and so forth. But if the both of them are moving, then you have this general equation over here. All right, so we have a couple of examples where we can see, let's say, how all this thing works. So we have a driver travels northbound on a highway at the speed of 25 meters per second. A police car traveling southbound at the speed of 40 meters per second approaches with its siren producing sound at a frequency of 2500 hertz. So what frequencies does the driver observe as the police car approaches? All right, so then what we do here is this. So we can say, all right, we are given, the speed of the observer as 25 meters per second, and then speed of the source, because the source of the car, right? So the siren of the police officer, right? So it's 40 meters per second. And original frequency is 2500 hertz. Now, because both of them are moving, then we use basically the more general equation. So F prime equals V plus VO over V minus VS and times the original frequency. Now, both of them are moving. That means this is 343 plus something and then 343 minus something, right? Those are not zero. But here's the thing, again, because thing like this, observer is moving, going toward the source. That means its quantity is positive. So it's plus 25 meters per second. And then the source is moving toward the observer. That means it's plus 40 meters per second. And then times 2500 hertz. Which means what you end up doing here is, you basically have 343, plus 25 and 343 minus 40 times 2500. And then F prime here is 3040 hertz. Okay, or 3 kilohertz. Okay. This is for part A. Let's look at part B. It says, what frequency does the driver detect after the police car passes him? All right, so in that case, what we do here is this. F prime equals, again, V plus VO over V minus VS times F. So then again, there's going to be 343 plus and then 343 minus. But in this case, because the observer is moving away from the source, so negative 25, and also the police officer basically moving away from the source, from the observer, then negative 40. Then this is 2500. And then what we're going to get here is 2.08 kilohertz. That means 2000, which is less than the frequency. For the part A, we see more than actual frequency. Here we see less than actual frequency. Let's look at part C. It says repeat part A and B for the case when the police car behind the driver and travels northbound. Okay, that means the observer is moving northbound and the police officer moving northbound, but the first one is behind it and then passes and then goes in front of it. All right, so let's look at doing in terms of the first one, which will be F prime is equals to 343 plus over then 343 minus then times 2500. Let's see what we get. All right, so remember, so if for this case, right, so here's the observer and then here's a police officer. See, the observer is moving away from the source, but police officer is moving toward the observer. Then this is negative and this is positive. And if I calculate, I'm going to get 2.62 kilohertz. Then the last one is this, right? So that means now police officer is past the observer. So this is police officer, and then this is observer. So then this is 343. And because this time observer moving toward the police officer, so it's plus 25, 343 now, but police officer is moving away from the observer, so negative 40, then 2500. So we're going to get 2.4 kilohertz. So that's basically the answer that we're going to get from this one. All right. So let's look at the last example here. All right, so what we have here is this, basically. A bat moving at 5 meters per second is chasing a flying insect. if the bat emits a 40 kilohertz chirp and receives back an echo at 40.4 kilohertz, what is the speed of the insect? And will the bat be able to catch the insect? All right, so let's see what we have. So basically this is an example where there's a, reflection, right? So, or, like echo, right? Basically reflects off of the source. And that's basically how the bat, catches the insect, right? So sends a sound wave, and the sound wave is reflected off of a, let's say, insect. So then they can see, let's say see where the insect is and then go and catch them. So that's kind of, what we're gonna do. So, all right, so here we have a couple of things. So let's say, again, going back to that equation, f prime is equals to v plus v observer over v minus v source times f. So in this case, in a way, we have, two things, right? So we have f1, which is the, let's say, the original frequency. So then f1 is 40 hertz. And then you have f2, which is 40.4 hertz, which is basically the perceived, right? So, the frequency by the meter. And we first have to calculate the frequency received by the insect, okay? So, and from the insect's point of view, V observer is equals to negative V insect. So like, let's say, so in that case, which is at this point, we don't know, let's say, the unknown speed of the insect away from the source. So, and this 5 meters per second, which is basically the bat is moving, right? So with respect to then the insect, it's then going to be negative 5 meters per second. So in any case, so the idea here is this. So I can say then f prime is equals to 343 minus v insect over 343 minus, this 5, meter per second, right? And this is times 40 kilohertz. This is basically because the insect, right? The bat is moving toward the insect, right? So then its speed is basically positive. All right, so let's, leave it like this. And then we're going to talk about the wave reflected by the insect, right? So the wave reflected by the insect, and, basically, in this case, the bat is the observer, right, for that one. Or the bat is basically receiving that. So, and then I can say f prime is equals to 300. So let's call this equation 1. Let's call this equation 2. So 343. Then in this case, basically, because it is moving away, so then becomes plus 5 meters per second. And then this is 343 because let's say the bat is the absorber and, insect moving away, right? So then 343. And let's say minus, right? So that technically, it's become like, let's say VI, let me put it like that. And this is then in terms of, actually, this is what we already hear, right? This is actually we already hear. And the original frequency is what is reflected off of. So basically something like this. Let me put this here, make it a little bit. That means what the bat hears is 40.4 hertz for whatever the, let's say, the assuming, right, the insect is producing, but the insect is not producing, it's just the insect is reflecting, right? It's echo, but then it is f prime. So that means whatever it receives, it basically re-emits the insect. And then when it reaches the bat hears it as 40.4 hertz. Okay. So then basically from here, then what we do is pretty much replace this with all of that. For f prime, right, in equation 1, we do the substitution and just basically put that in terms of for the f prime. So once I do it for the f prime, then I can just basically do this calculation. That means, what I get here is 40.4 hertz equals to Then I have 343 plus 5 over 343 minus V. But in this case, remember, so technically it's moving a wave, so it's negative, so I can just put this as a positive here. And then here I can say then 343 minus V insect. And then this is then 343 plus Vx. Or, so not Vx, V insect. Okay, so sorry. I'm doing this, so minus 5, sorry. This is minus 5. And then times 40 hertz or kilohertz. Okay, so that means, we end up with that. Okay, that means, I just took this equation, right, for f prime and, basically replaced it there. Okay, and then just basically we're going to do some rearrangement, some tedious work, right, rearranging and solving for VI. So V of the insect then will be 3.29 meters per second. Okay. So this is basically what we can do in terms of for this part A. And for the part B, it says, will the bat be able to catch the insect? Well, one thing we can see is that the bat is moving at 5 meters per second and the insect is only moving at 3.29 meters per second. So definitely, be able to catch because, it is moving at roughly 1.7 meter faster, right, than the insect. So they eventually be able to catch the insect. All right, so that's basically the answer for that. So for B, you can say then yes, we'll be able to catch the insect. All right, so this concludes then chapter 13.